Hello, welcome to this video produced as part of the Further Maths Support Programme's material for A-Level Maths and Further Maths. This one is about the components of acceleration in circular motion. Consider a particle moving around a circular path. We found in the past that it's convenient to describe its speed by considering the rate at which it's turning, the so-called angular speed. There's the diagram you'll have seen before, with the notation theta dot, which is simply a shorthand for d theta by dt. It's less clumsy and it's easier to use, so long as you remember to keep the dot clear. Omega is sometimes used as an alternative as well. We can write these together. D theta by dt, the rate of angular change, is equal to theta dot, or is equal to omega. Now what happens if we're dealing with a situation in which the angular speed is variable, and so the speed at the circumference is also variable? Now there's the familiar kinematic relations from the previous slide. We need to add to this the accelerations. The linear speed v also varies, and that means there's an acceleration in along the tangent as well as towards the centre. So the radial acceleration is still the same, v squared over r, or r theta dot squared. But this time we have a tangential acceleration, which is the rate of change of v, or v dot. So there we have v dot. It's bound to be r theta double dot if r is a constant, which it is for a circle. And r theta dot squared has the alternative notation v squared over r, which we mustn't forget. So that's the new bit of knowledge, that v dot, which is the same as r theta double dot, is the tangential acceleration. There we have the kinematic information again for accelerations. Let's now consider what happens if we know theta is a function of time. Well, a simple example is that a particle p moves in a circular path with radius 0.6 meters, and the angle theta at the centre is 3t squared, where theta of course is measured in radians. We're asked for the radial and tangential components. Well, there's the information gleaned from the question that we need to know. So from this we can deduce that theta dot is equal to 6t, and theta double dot, the angular acceleration, is equal to 6. So on that basis, r theta dot squared will be equal to 0.6 times 6t squared, and r theta double dot will be 6 times 0.6. So those worked out simplify to 21.6 t squared and 3.6 respectively. So we can state the answer in context with the units. Well, that's a simple case where theta depends on t. Normally it won't, so we need to consider what to do when that's the case. A bead A of mass, be careful, 0.01 kilograms, is threaded onto a smooth circular wire. That means no friction. And the radius is 20 centimeters. Careful again, that's 0.2 meters. The bead's projected from the lowest point with speed 3 meters per second, and we want to find the radial and tangential components of acceleration when the bead's at B. Where on earth is B? Well, there's the diagram which tells us. Now, in addition to what's in the question, I've also marked V for the speed at V, because we'll need that as an intermediate quantity. Now, this is a situation which is analysed by energy most conveniently, because of the forces acting. Here's the force diagram. There are only two. The normal reaction from the wire. There is no tangential force because we're told that the wire is smooth, and the only other force is the weight. Now, thinking of energy, the point of application of R is always moving at right angles to its direction along the tangent. That's how we've got V like that. So R will do no work. The only other force is 0.01 g. That certainly does work, but we can measure that by energy. So this is a conservation of energy situation, as we've seen before. So let's do an energy analysis. We'll take the zero level for PE as down at the level of A. Now we'll need to know how much higher B is above A. So if we draw a horizontal line across there, that will give a right angle between that vertical radius and the horizontal. So using 0.2 cos 60 and knowing that cos 60 is a half, the drop from O to the level of B is 0.1, so the drop from the level of B to A is also 0.1, so that we make up the full radius of 0.2. Now that allows us to do an energy analysis. So if we take the final energy, it will be kinetic, a half times the mass times the velocity squared, plus the potential energy, which is 0.01 the mass times the gravity times the height above the zero level, which we calculated as 0.1. And that will equal the initial energy, no potential energy to start with, just kinetic, so a half times 0.01 for the mass times the 3 squared, which is 9. Now immediately we can see that the 0.01s cancel out. We might have expected that. And we can multiply by 2 to get v squared plus 0.2 g. That's a 2. I'll cross that out and start again. 0.2 g. That equals 9. So v squared is 9 minus 0.2 g, and we're using g equals 9.8. So 2 times 9.8 is 19.6, so 0.2 will be 1.96, so it's 9. That's a 9, doesn't look like it, does it? 9 minus 1, I said 19.6, so 1.96. 9 minus 1.96 is 7.04. So our v squared value is 7.04. So if we go to the following page, that summarizes what we've just worked out. V squared is 7.04. Now we want to go on to find the radial and tangential components. So the radial one first. Now the radial one will use the alternative formulation, which is v squared over r. So the radial acceleration will be the 7.04 for the v squared divided by the radius, which is 0.2. So that gives us 35.2. So we can give the answer to that in context. The radial acceleration is 35.2 meters per second squared. Now for the tangential acceleration, we've got two possible ways of doing it, one complicated and one simple. Let's go for the simple. But briefly, the complicated one will be to take the energy expression, which gives us v squared, and differentiate it. That will be complicated, so we won't do that. We'll do it instead a much simpler way, which is to look at the force diagram and say that from the circle up above, the 60 degrees will appear there. So the angle between the gravity and the tangent is 30 degrees. So if we resolve along the tangent, we find that r doesn't contribute because that's a right angle, of course. So we can say that 0.01 g times the cosine of 30 must equal the mass 0.01 times the acceleration, which is v dot. Only it's minus v dot because the acceleration, as you see, is directed in the opposite sense to the component which we've just obtained. So from that we can say that v dot is equal to minus g cos 30. That's cancelling that 0.101 again. And g we know is 9.8. So we've got minus 9.8 root 3 over 2 for cos 30. Now my calculator gives that as minus 8.4870 dot dot dot. So that will be minus 8.49 to 3 significant figures. So that's what the tangential acceleration is there. So we can state that in context with the units 8.49 meters per second squared, and I've taken account of the sign by saying it's a deceleration. So that brings us to the end of this video. The next one is on the motion of a particle. We're thinking of vertical motion on the particle at the end of a string and when it may fall out of the circle.